Hi class, in this video here, I want to do a real quick brief introduction to section 4.4. The textbook's going to go into a lot more detail than what I'm going to talk about. I just want to give you like the real basic idea. And this section is called Soothing Symmetry and Spinning Pinwheels. And so the idea here that we'll talk about, and again in much more detail in the text, is can a floor be tiled without any repeating pattern? So what I mean by that is like, imagine you have this floor you want to tile. Pick a shape. Okay, and every inch of the floor needs to be covered. Okay, you pick a shape, and then can you put that shape down on the floor, and then somehow building off that shape, put that same shape in some other pattern next to it, and then keep repeating it. Take that shape, put it next to it somehow, and then again next to it somehow, such that when you look down at the floor, you'd never have any repeating pattern. I don't know. All right. So the main questions from this, it has to deal with symmetry. Okay. And so what is symmetry? So the way the textbook looks at it is we sense symmetry when small portions of a pattern are repeated elsewhere in an overall pattern. Like here, if you look here, look at these two tiles here, and then it's a repeat, and then a repeat, and then a repeat, and then a repeat. You can see the symmetry here, the pattern repeating itself. Okay. And then it's like as you get four of them, right? Then it repeats itself right here, and then it repeats itself right here. Or if you want to look at, you can see this right here. Then it repeats itself right next to it. All right, that's what we think about symmetry. Then there's this concept called what is rigid symmetry. We'll say that rigid symmetry of a pattern in a plane is a motion of the plane that preserves the pattern but does not shrink, stretch, or otherwise distort the plane. So what that means is if you like, think about this as our original pattern. If you shift it or rotate it or flip it, it still has the same like overall pattern shape, okay, but it doesn't change it, doesn't distort it, okay, it doesn't change its size. Then the textbook's going to talk about what is symmetry of scale. And we'll see that a pattern in the plane has symmetry of scale if it's scalable, or symmetry of scale or is scalable, excuse me, if the tiles that make up the pattern can be grouped into super tiles that still cover the plane, and then if scaled down, can be rigidly moved to coincide with the original pattern. And like I love this photo in the textbook kind of illustrates it here. Here's our original pattern, and then when we stretch it, you can see the pattern is still maintained, but then like this square up here has the overall pattern and so on. So it takes the original pattern to create new super tiles, which then still maintain the overall original pattern. All right, so then it goes back to this question here. We kind of understand a little bit what the two type of symmetries are. Is can a floor be tiled without any repeating pattern? All right, so basically this is the idea of what's called a pinwheel pattern. So where would you start to build a pattern that has a symmetry of scale but no rigid symmetry, right? So like you're scaling it up, okay, but the pattern doesn't repeat itself. Okay, that's what we're saying. All right, so for a pattern to have symmetry of scale, we must be able to group the tiles to create super tiles of the same shape as the original tiles, like you see here. These tiles are creating end up being the building blocks of a super tile. Okay. So then in the case of to do this, we use this thing called the pinwheel pattern. And the basic tile is pretty simple. It is just a right triangle with one leg of the triangle twice as long as the other. And we'll call this a pinwheel triangle. And so we'll use the Pythagorean theorem. So this relates back to like the golden ratio. You'll start seeing some numbers that are really common. So by the Pythagorean theorem, we see that the pinwheel triangle has legs of length, because remember, one is twice as long as the other. So we'll just say length 1 and 2, so twice as long as the other. And then by a squared plus b squared is equal to c squared, the hypotenuse has to be the square root of 5. Well, if you think about what's the golden ratio, 1 plus the square root of 5 divided by 2, these numbers are coming up again. So those specific proportions are chosen because 5 identical pinwheel triangles can be assembled to form a larger pinwheel triangle. Okay, that is another right triangle with one leg twice as long as the other. And we'll call that large pinwheel triangle made up of 5 smaller pinwheel triangles a 5-unit pinwheel triangle. What the heck does that mean? Okay, so look, here's our first triangle. All right, and then remember, it has one leg 2, one leg 1, and the hypotenuse square root of 5. All right. If you take this and look, you build off it, okay? You use the same shape, all right? And you use, the idea of like, what can I, putting pieces, tiles right next to each other, right? You can construct a new triangle, okay? And this new triangle is another right triangle. And this length right here is half the length of the longer one, or this longer side is twice the length of this one. So you've used the original triangle to create another triangle, okay? If you do that, and then all of a sudden start with one, make 5 triangles, okay? And then use that one you just constructed to form another triangle, okay? You see how you're using triangles to build bigger triangles? All right, if you keep doing that, you will get a pattern here, all right? So I started here, and then look, here's the first one that I built, okay? And then from that, here's the second one that I built. It's embedded in there, okay? If you do that, you're going to get a pattern that is symmetry of scale, but there's no rigid symmetry. And this right here is what's called the pinwheel pattern. And again, in the textbook, you'll spend a lot more time talking about this and learning about it. All right, let's just do one mindscape so you can see the idea of this like pattern in tiles. Okay, and so here's one mindscape from the textbook. Okay, and it's about to tile or not to tile. So which of the following shapes can be used to tile? Like imagine a floor, okay? And you want to cover every little piece of the floor, okay? So which one of these could be used to tile an entire plane? Okay. Well, look, you could put squares next to each other. That would be no problem, okay? And that would cover everything up. Triangles you could do, right? Because what you could do is you could just take this triangle and put it right here where my mouse is, and you've got a rectangle, and then you could just fill up rectangles, okay? The star you couldn't, right? Because like if you try to put a star next to each other and you try to pad tile, you would end up with little spaces. So you can't use star patterns to tile an entire floor. That's no good. The same thing with this triangle with a hole in it. Like you can't, like if you were to try to put another piece next to it, you would still have this hole in it. Okay. The tricky one is this one here. Like how could you use this to tile a floor? And it's like, look, let me start with a piece. And then put another one. You see it slides right in there. And then look, I'm going to put another one in there. And then put another one in there. Look, now it's like I've got this kind of like rectangle thing, but these things are starting out. Well, let me take this shape and then put it in. And look, it fits right in. And then I could take this pattern and make another big pattern in it, and they will all just fit right in perfectly. So this one might not look like it, but you could use this shape to tile an entire floor. All right, I know this was a real quick introduction, and it is a confusing concept, but please take some time to read through the textbook. It goes into much more detail, and as always, I am here to help.